In this problem, we're being asked to sketch the graph of f of x equals x minus 3 divided by x squared plus 2x minus 15 by finding the intercepts, asymptotes and holes, the domain, where it is increasing, decreasing, concave up, concave down, any relative extrema, and points of inflection. We'll start by finding the asymptotes, holes, and domain. So the horizontal asymptote, if we recall, to find a horizontal asymptote for a rational function, we're looking for the limit as x approaches infinity or negative infinity of our function. And when dealing with rational functions and looking at the limit as x goes to infinity, as x gets very, very large, the end behavior of the two polynomials in this problem are taken over by the leading term. And so in order to find this limit, we could instead look for the limit of x over x squared. Just focus on the leading terms, because as x gets very large, subtracting 3 doesn't make a difference. Adding 2 times a number minus 15 doesn't really make a difference when x becomes extraordinarily large. And so when we simplify this, this is 1 over x, and the limit as x goes to infinity of 1 over x is 0. So that is our horizontal asymptote. Now for vertical asymptote and holes, what we're going to do is factor and simplify, and note what ends up being factored out and simplified out, and then what remains. So x minus 3 cannot be factored. X squared plus 2x minus 15 can be factored. The x squared terms need to be x times x, and then 15, we have a couple of options, 1 and 15, or 3 and 5, but we want to focus on ones that maybe in some combination give me a 2. So I'm going to choose the 5 and the 3. And so when I add my outers and inners, they need to add to positive 2. So the larger number, the 5, needs to be positive, and the smaller number, negative. And one needs to be positive and negative because when I multiply them together, I need a negative 15. And so now I note that I have an x minus 3 and an x minus 3 in the numerator and denominator. So that's equivalent to 1. But when I do that, it is removing a 0 of the denominator, and that means we have a removable discontinuity, or a hole, at x equals 3, which would make the denominator and numerator 0, but now that it's simplified, it is no longer there, and hence the name removable discontinuity. And then we look at what remains, the x plus 5. That tells me that negative 5, because when I plug that in, will cause the denominator to be 0, but not the numerator. This is a vertical asymptote. Okay? And from here on out, this is going to be the function I'm going to work with. But remember that x cannot be equal to 3, right? Because we're really, always remember, we are sketching that function, but when simplifying, it means we are the same shape except for at 3. There is a hole, right? So those two graphs, the x minus 3 over x squared plus 2x minus 15, have the exact same shape, except at positive 3, there will be a hole, that removable discontinuity. But otherwise, they're exactly the same. So now that I know I have two discontinuities, one removable, one non-removable, my domain, by looking at my number line in those values, so here's negative 5 and 3, I have discontinuities there, which means I can go ahead and use anything in between there, or anything to the right of positive 3, and anything to the left of negative 5. So when I write this as my domain, it's negative infinity to negative 5, and then from negative 5 to 3, and then from 3 to infinity, right? We're not including negative 5 and 3. So those three intervals will come up again and again in our next work. Okay, so next we're looking for y-intercepts and x-intercepts. And remember, we're going to use this simplified version, and remembering also that still x cannot be equal to 3. So my y-intercept is we plug 0 in for x. So f of 0 is 1 over 0 plus 5, which is 1/5. So my y-intercept is 0, 1/5. My x-intercept means I set it equal to 0 and solve for x. And so if I try to solve this, well, there's nothing. This would be claiming that 0 is equal to 1, but that can't happen. So there is no solution. A fraction is equal to 0 when its numerator is equal to 0, and a fraction is undefined when its denominator is. But we're looking for where is it 0. So that would only occur if the numerator was, but the numerator can't because the numerator is a 1. So there's none. Okay, so we have a y-intercept, but no x-intercept. Next, we're going to be using the simplified version of our function. But always remember where we have a hole, right? So we're always going to carry with us, yeah, we're going to use 1 over x plus 5, but we have to remember that we can't let x equal 3. So I'm doing the derivative, so I'm quotient rule, a little bottom d top minus top d bottom over bottom squared. So x plus 5 is the bottom times the top, the derivative of the top. 1 is the top, the numerator, and its derivative is 0. And then minus the top times the derivative of the bottom. The derivative of x plus 5 is, in fact, 1. And when I clean that up, I get 0 minus 1 in the numerator, gives me a negative 1, and I have the x plus 5 squared in the denominator. So I want to know if there are any critical values of this function. So I first ask, all right, where is the derivative equal to 0? And again, the derivative is equal to 0 when the numerator is equal to 0, because it's a fraction, right? This function is equal to 0 when its numerator is, but its numerator cannot ever be 0, so it's 0 nowhere. However, do we have anywhere where it's undefined? So that would be where the denominator is equal to 0. Well, this would be equal to 0 if x is equal to negative 5, but that's our vertical asymptote. So that means we have no critical values, no values that are in the domain of our function, our original function. Right? Here is the domain of our original function. There are no critical values, no values where the derivative is 0 or undefined that are in the domain. There's either no solution to the derivative equals 0, or the only solution to the derivative undefined happens to be at a vertical asymptote. Okay, so that means no critical values, no relative max or min, because those are the only places we can have a max or min is at a critical value. So I'm still going to use this information to find where I'm increasing and decreasing. So I have our domain set up here across our top number line, right? So negative infinity to negative 5 to 3, 3 to infinity, and then I pick some test values. So a number that lives in negative infinity to negative 5 would be a negative 6. And a number that lives in negative 5 to positive 3 is 0. That's a good candidate. And then a number that lives in 3 to infinity, I'm going to pick 5. So then I'm going to find out, well, what is the value of the derivative at negative 6? And if I plug that into the derivative, I get negative 1 over negative 6 plus 5, which is negative 1, and then negative 1 squared is positive 1. So my result is negative. That tells me my function is decreasing on that interval. So it's decreasing up to that vertical asymptote, right? So we kind of can envision the behavior that's going to go on there once we hit that vertical asymptote. Okay, the next I'm going to check the sign of the derivative at 0. And again, I plug that in, so it's negative 1 over 0 plus 5 squared. 0 plus 5 squared is 25. That is, again, negative. So once I come after the vertical asymptote, I pick my pencil up, go to the other side, it is decreasing. And then I'm going to check, what is the sign of the derivative in the interval from 3 to infinity? Well, it would be the same everywhere, including at 5. So I plug 5 in. Again, I get negative 1 in the numerator, and then 5 plus 5 is 10. 10 squared is 100, so I am still negative. So notice what's happening here. After my vertical asymptote, I am decreasing, and then I hit the hole, and then I continue decreasing. Okay. We're going to go ahead and find our concave up, concave down points of inflection. So I've got my first derivative there, negative 1 over x plus 5 squared. And then I'm going to do the work to find the second derivative. So second derivative, remember, is bottom times the derivative of the top minus the top times the derivative of the bottom. And there I'm using the extended power rule, the chain rule, right? Bring the 2 down. Bring the 2 down to the front, subtract 1, and then scoop up the inside and find the derivative and multiply. So that's how I got 2 times x plus 5 to the first times 1. All over the denominator squared, so x plus 5 squared squared. So if I clean up that numerator, x plus 5 squared times 0 is 0, minus a negative 1 times 2, that gives me a positive 2, times the x plus 5, divided by x plus 5 to the fourth. And then I can see I have a factor of x plus 5 in the numerator and 1 in the denominator. So if I factor one of those out and simplify, reduce, then I'm left with just the 2 in the denominator, or 2 times 1 in the numerator, 2 in the numerator, and then I'm left with 3 factors of x plus 5 in the denominator. I go through the same process. Where is this second derivative equal to 0? That would be when the numerator is 0, and that never happens. Where is the second derivative undefined? That would be when the denominator is 0, and that is at x equals negative 5, which is the vertical asymptote. So I have no values that make the second derivative 0 or undefined that are in the domain of my function. So since there aren't any, that means no points of inflection. But I can still use the second derivative to determine where I've concave up and concave down. So just like I did with the first derivative, I'm using the second derivative as a tool to tell me what's going on in that interval. So again, I'm picking test values, one that lives in negative infinity to negative 5, I chose negative 6. One that lives in negative 5 to 3, I chose 0, and one that lives in 3 to infinity. So whatever happens at those test values is indicative of what's happening in that entire interval. So I plug each of those values into my second derivative, and you can see the results there. F double prime of negative 6 gives me a result of 2 over negative 1, so that's concave down. F double prime of 0 yields 2 over 125, that's positive, that tells me it's concave up. F double prime of 5 yields 2 divided by 1,000, which is positive, so that's still concave up. I'm going to take all of this information and put it together to sketch the graph. Okay. All right. So from our algebra work, right, there was no x-intercept, but there was a y-intercept at 0, 1/5. So I plotted that there on my graph. The rest of it, I had these intervals that appeared every single time. So I used those intervals, right? Negative infinity to negative 5, negative 5 to 3, 3 to infinity. The domain, right? And there weren't any places where I had turning points, right? Relative max or min or points of inflection. So I'm just going to use those intervals. So on each of those intervals are the characteristics we found. On the leftmost interval, it's decreasing and concave down. So it would have that shape that's listed there. You know, curved down and decreasing, going downward from left to right. In the middle interval, decreasing but concave up. So decreasing but having that slight curvature going upwards. Right, so it has a slight curve upwards, and then I hit that hole, right? Vertical asymptote at negative 5, the hole at 3. You might say, well, how did I find out that the value was 1/8? Well, it's actually a lot easier than you think. Remember, our simplified version is 1 over x plus 5, and we said this looks exactly the same, right? Our original function, let's remind ourselves what our original function is, x minus 3 over x squared plus 2x minus 15. So that's what this is the graph of, and we said it looks exactly the same except for the hole at 3. And where does the hole live? The hole lives at 1 over x plus 5 when x is equal to 3. Which is 1/8. So that's how I knew that the hole was at 3, 1/8. So I plotted that there, right? 3 comma 1/8. Also plotted my vertical asymptote, so I did all of that first. Everything that's in non-pink. So the yellow, the green, the blue, I plotted all of that first, and then I plotted my y-intercept, and then I used the information that I had here, right? So concave down and decreasing, and I have a horizontal asymptote, so I knew I had to be flat, and so it had to be either here or here on this side. But since I had to go down toward the vertical asymptote, that tells me that I'm on this side. The other way to tell is plug in, right? What is f of, let's say, -10? Well, that's going to be 1 over -5, so that would be somewhere down there, right? So it's going to be below the horizontal asymptote and then going downward and curve downward past there to the vertical asymptote. And then remember, we pick our pencil up and we start on the other side of the vertical asymptote, and it's telling me I'm decreasing in concave down. So I know that I'm decreasing in concave down. And again, how do I know it's up at the top and not starting, I don't know, someplace else? Again, a quick check, pick something to the right of -5, so f of, let's say, -4. Plug that into 1 over x plus 5, that's 1 over 4 minus 5, that's 1. So -4 is approximately 1. Didn't really do this to scale, so you'll have to forgive me there, but we still get that the point is above the x-axis. So then I know that my graph goes through here, goes through the y-intercept, that I also know that that's, above the horizontal asymptote, so that's another indicator. And then I go past my hole and go out to the other side for the horizontal asymptote.